Professor Kurian completed his MTech and PhD degrees from IIIT-Bangalore. Post that, he worked as a postdoctoral researcher at Purdue University. His works at Purdue focus on ultra-low power biomedical wearable designs, human body communication, mostly related to the topic which we are going to learn from him today. He also worked with Cypress Semiconductors for 5 years, where he developed first of its kind capacitive touch sensing interface solutions, which go in most of the mobile phones or any LCD touchscreens and things like that. Professor Kurian is also author of 6 journal papers, 7 conference papers, and many technical articles with Cypress. He is a passionate hands-on system design engineer, and his present research interests include wearable systems for Internet of Bodies, low-power secure communications, and hardware security. His vision is to set up and lead a best-in-class embedded systems lab and fab lab to support student research projects. So title of the talk today means Introduction to Internet of Bodies and Human Body Communication. Very few VLSI research groups work in this domain. And there are lots of opportunities and problems to address. We are looking forward to learn from you, Professor Kurian. Over to you.
Thanks, Professor Mani, for the introduction, and thanks, Professor Amurtha and Sujit for inviting for the talk. And thanks for you coming here and attending the session. So the topic that I'm going to present is about Internet of Bodies and man-body communication. This is a topic many researchers are working in this area, particularly in the area of Internet of Bodies. And a small number of research labs are also working in the area of man-body communication. So I'll talk about what man-body communication is. By the term human-body communication, you might have some questions about what it means. And many times people think that it's a complicated mode of communication. It is not. It is very easy to understand. And there are difficulties in its implementation. That's why human-body communication is not so popular. So I'll talk about, in the presentation, I'll talk about at a high level what an Internet of Body is, the concept of Internet of Body, what are the research directions in Internet of Body. Then I will move on to talk about human-body communication, where human-body communication fits in the Internet of Body architecture, how human-body communication works, what's the problems with human-body communication, what are the research directions, and what are the applications of human-body communication. So this will be a high-level talk, a little technical details, but enough to help you understand about how it works. Okay, so most of you know about Internet of Things. So the idea is that there are things around us which senses information from the environment. This information is communicated among themselves or to some remote servers, where this information is processed to get some meaningful output from using that information. What if these things that you see around us are on the body? That is where the concept of Internet of Bodies comes into picture. So Internet of Bodies is a subset of IoT. Just like you say that industrial IoT is a subset of IoT, Internet of Bodies is a subset of Internet of Things. The difference is that the things that you're going to talk about, the physical things, are going to be on your body. Okay, so why do you want these things to be on your body? To give you an example, say, for instance, you have a ECG node on your body. Let us assume that you have an ECG node on your body. The advantage of having a node on your body is that this node can continuously scan your ECG and send this information to some cloud server where it can be processed to figure out if there is some kind of anomaly that is happening to your heart state. Okay, so if you look at current situation, if you want to take an ECG, you have to go to the hospital and take an ECG, and that happens once in a year or twice in a year. Some of the smartwatches allow you to do ECG, but if you look at Apple smartwatches, you have to touch it and then take the ECG. But the moving forward, people are believing that there will be nodes on the body that will be doing continuous ECG measurement. So it will be like a patch, like a band-aid sized patch on the body, which will continuously perform ECG measurements and then transfer it to the cloud. Now, what is the advantage? The advantage is that some of the diseases, heart diseases, it is very difficult to figure it out by just doing one ECG measurement. Say, for instance, there is a heart disease called arterial fibrillation. The idea is that the heart rate varies over a period of time, and that doesn't happen very often. So it happens once in a day, or maybe a couple of times in a month, and it is very difficult to figure that out if you go and do an ECG once or twice in a hospital. So it is greatly beneficial if you have an ECG node on your body. The same is the case with if you have multiple other biomedical nodes on the body. So if you have an EEG or a blood pressure unit, it can continuously track your sugar levels, and the doctors or you yourself can take some kind of informed decision. You have more data to work with. Okay, so yeah, so this is the idea of the applications of IOB. You can do a 24/7 patient monitoring. Okay, which is not possible in the current situation. Most of these are non-invasive in the sense that you don't need to place a node inside your body, but the nodes which are inside your body also come under the paradigm of Internet of Bodies. The Internet of Bodies, by definition, it is all the nodes, interconnected nodes on or implanted on your body. Precision medicine. So the idea of precision medicine is that if you know exactly what the problem is for a particular person, you can fine-tune the medication according to that individual's health status. So that's the concept of precision medicine, and the way it allows you to fine-tune the medication is you have more data now to play with. This is something that may not be very interesting to Indians, but the idea is that you can have personalized health insurance if you are in countries like US, where if you are staying fit, the insurance amount will be lower. If not, you'll have to make a higher amount premium. Okay, so it is beneficial both to you as well as to the insurance companies. Yeah, so the idea is that if you do a continuous and long-term monitoring of your health state, you can easily you can detect the diseases early, even before they pop up. So that is one of the reasons why people are looking into having nodes on the body. So I'll just go through some of the research directions in this area, and then I will go and explain about human body communication. Ultra low power wearable designs, if you look at the nodes on the body, they have to, the concept of having the nodes, IOB nodes on the body is that they have to work for a long durations of time. And that is only possible if the power consumed by these wearables are very small. Okay, most of these time, these wearables are battery operated. They are not connected to the supply. So they have to consume significantly lower amount of power so that they can sustain that operation for a long period of time. And one other reason why you want the wearables to have ultra low power consumption is because you want the battery size to be very small. If the battery size is large, it becomes very difficult to, if it is bulky, it is difficult to have that patch on your body. People are working in this direction, particularly people who work in the IC design, like Professor Manikandan, they work in this area. They try to bring the power consumption to microwatt to nanowatt. The second topic that people are nowadays looking is energy harvesting. How do you harvest energy and operate these wearables? And one of the elements of harvesting energy is through the body. I mean, you can use the body temperature to harvest energy. So the body maintains a temperature of about 37 degrees Celsius, which is typically higher than the surrounding temperatures. So there is a delta T. And if you can make use of that delta T, it's possible to harvest energy from it, and we can operate these wearables for a long period of time. And we call that concept called perpetual operation. So you don't need a battery to operate it. And there is some advantages for battery-free wearable designs. Sometimes what happens is that this battery, because it has chemicals inside it, it can react with your body, particularly if these nodes are implanted inside your body. And many times we don't want that to happen. So people are nowadays focusing on having nodes which can work without the battery. And the only way it can work without the battery is if it has some kind of mechanism to harvest energy. So people are looking into how to harvest energy from body temperature, how to harvest energy from the vibrations of the body, and so on. This is another area. People are working on textile sensors. So how do you embed these electronics into the cloth? So that, for instance, if you want to do the ECG measurement, you don't need to have a patch. It could be embedded. The electrodes could be embedded on the your T-shirt so that it can monitor the ECG. So a group of people are also working in this area, particularly people who works on the devices side and sensor side. This is a very interesting topic. This is something that I'm going to explain. Secure and low power communication. So if you look at the nodes, they are sensing your body information, health information, and it needs to communicate this information to other nodes as well as to the cloud. Now, the data that these nodes are communicating is very sensitive. It's your personal health data, and you don't want this data to fall into wrong hands. So the communication has to be very secure. And further, the amount of power that these communication methods should consume should be significantly lower if you want this wearable to last for a long period of time. So there is a growing interest in designing secure and low power communication methods. And one of the secure and low power communication method is called the human body communication, which I'll be talking about. There are other communication methods also. For instance, we have been working on visible light communication. Ritesh, I was working with Ritesh and Kavya on that. We can use visible light to communicate data from the wearables to for instance, a smartphone. So coming to the applications of Internet of Body, healthcare, that's something that I explained in the first slide. It can also be used for secure authentication. So for instance, you have a node on your body, it can be used to unlock a door. So you don't need to have a biometric assay. So you are not sharing your biometrical credentials, but there is some node which is sending some data to the body, and you're unlocking the system. And it can also be used for human-computer interfaces. Say, for instance, if you want to move a slide or change or interact with the machines, then some of the nodes which are positioned on your body might be able to help. Okay, so that's about Internet of Bodies. And let me focus on the communication part. Okay, so when you're designing a wearable, typically when you're designing a wearable, 50% of the power goes into communication. So if you have a wearable for ECG or for a blood sugar monitoring, there's a sensor part to it which monitors the ECG, and the processing components are there. Then there's a communication component. So the communication component today consumes about milliwatts of power. If you look at Bluetooth or Wi-Fi, it consumes significant amount of power in terms of milliwatt. But if you look at the IC designs, the sensors and the processing parts can be done in microwatts of power. So the bottleneck in today's wearable design is communication. And that's one part. The second part is if you use traditional communication technologies like Bluetooth or Wi-Fi, they are radiative technologies. So to send the data, they radiate signals all over the person's body, and it can be easily hacked. Okay, so for instance, Bluetooth, it has a range of about 1 meter, and anyone who is in that vicinity can hack into that Bluetooth signal and possibly decode the data. So these are the two main problems. Eavesdropping is a problem if you are using Bluetooth or Wi-Fi, and second part is the amount of power it consumes. And the amount of power it consumes is directly dependent on the size of the wearable. So if you are using a Bluetooth or Wi-Fi which is consuming milliwatts of power, and if it has to last for a long period of time, it needs a bulky battery. So the wearable design will not be compact. To give you an example, this is a wearable that you can purchase in US. It's a vital patch. It can do continuous ECG measurements, but the problem is that it works only for a few days, and after that you'll have to throw off or you have to replace the battery. So the solution to this problem, one of the solutions I would say, is human body communication. Yeah. For human body communication. Yes. So that's another that's another subject in itself. What will happen if you have a wireless device on your body for a long period of time? Yes. So that's also another area to think about. And so coming to human body communication, this is one solution to this problem. So there are many other solutions. One of the solutions, as I mentioned, would be if you use a visible light communication. And if you are using visible light communication, there won't be a problem of radiation affecting the body. The reason why people are working in the area of human body communication is because it consumes significantly lower power compared to Bluetooth or Wi-Fi, which is in the range of microwatts compared to milliwatts consumed by Bluetooth or Wi-Fi. And it doesn't radiate the signals all over the place. So it confines the signals within the body. So it is more secure if you compare it with radiative technologies like Bluetooth or Wi-Fi. So at a higher level, the way human body communication works is you have a transmitter which is on the body. So this could be a ECG node or a wearable. You have a hub on the body. Could be a smartwatch. And the wearable is transmitting data to the smartwatch. And it is using the body for communication. The signal is confined within the body. And here the body is being used as a channel for communication. Now, if you look at here, this is to contrast between the traditional method of communication and HBC. If you look at the Bluetooth and Wi-Fi modes of communication, you have a wearable here. You are radiating the signal all over the place. And you might have a smartwatch which can pick up the signal, but a hacker also can pick up the signal. And more than that, because you are radiating signals, and because you're radiating the signals, it consumes more energy than the case where you are sending the signals in a confined form. Okay, so the radiation is the reason why the power consumed by the wearables are significantly higher than the power consumed if you are using a human body communication method. Okay, to talk about the history of HBC, it is not a new technology. It is something that was proposed by Zimmerman in 1995. So it's a 3-decade-old technology. It is also known as intra-body communication. Some people call it body-coupled communication. This is one of the work that first described human body communications about personal area networks, near field communication. So the way it works is you have a transmitter here, which is applying some voltage on the body with respect to Earth's ground. I will give you a better picture to help you understand. And if you want to send some data, you modulate the voltage that is applied on the body. You change the voltage. You increase or decrease the magnitude of the voltage to send bit 0 and bit 1. And at the receiving side, you can read that data. Okay, so that's how the human body communication works at a high level. That's how it works. To make it more simple, to help you understand it in a better manner, this is what happens. So this is the simplified model of a human body communication. So you have a transmitter here sitting on the body. You have a receiver on the other end of the body. Okay, so the way it works is you have a transmitter block here. Okay, and there is a signal electrode where the signal is applied, where the voltage is applied, and there's a ground electrode for the transmitter. And this ground electrode of the transmitter is floating. It is not connected anywhere. Okay, and you are applying a voltage on the signal electrode with respect to the local ground of the transmitter. This capacitor that you see here is a parasitic capacitor. There is no capacitor that is being placed. It is a parasitic capacitor that exists. Similarly, if you look at the receiver side, you have an electrode which is in contact with the body, and the signals from this electrode is logged, that is V0. The ground here is also floating. It is not connected anywhere. Okay, so you have two devices. One device have the signal electrode on the body. Its ground is left open. The other device also has an electrode on the body. Its ground is left open. So what you see here as a capacitor CGTX and CGRX are the parasitic capacitors. So if you look at any point in the body, so I have a capacitor from my hand to the ground. So similarly, you have a capacitor here between one ground of the wearable and the earth ground. The same is the case with the HBC receiver. You also have a capacitance on your body, which is called the CB. Okay, so this is called the body capacitance. Now, what happens is that if you want to send some data, say if you want to send some data bit streams, if you want to send say bit 1, I will apply a voltage of 5 volt at this point with respect to this ground. Okay, and if I want to send a bit of 0, I will apply 0 voltage at this point with respect to this ground. Now, what happens is that the voltage that gets developed here, which we call it as VHBC, that gets divided between these two capacitors, CB and CGTX. So a portion of this voltage will be developed across the body with respect to the earth ground. And a portion of this voltage will get further divided between the CL, which is the load capacitor of the receiver, and the parasitic capacitor of the receiver with respect to the earth ground. So if you are applying a 5 volt, a significantly lower amount of voltage will be seen here. Now, if you don't apply voltage, you won't see much voltage. So that's a concept. That's how the HBC works. So all that you need to understand if you want to know how HBC works is the basics of parasitic capacitors and how the voltage gets divided between the capacitors. Is it clear? So if you look at the transfer function, the V0 by VHBC, you get something like this: CGTX by CB into CGRX by CL. Yes. Okay. Okay, so this will give more clarity. So this is a capacitor of the body, which it's a natural capacitor of the body, which is about 100 picofarads. Okay, and this is a parasitic capacitor. So if you have a wearable, it will have a ground, and the ground will have a capacitance to the earth. Similarly, just like we have a capacitance to the earth, which is CB, any device will have a capacitance to the earth's ground. So that is CGTX. So typically it varies. It varies with respect to the size of the wearable environment. And for now, I have taken it as 1 picofarad. Similarly, there will be a capacitor here, which is a parasitic capacitor formed by the receiver with respect to the earth ground, which can also be modeled as 1 picofarad. And there will be a load capacitor. So this is typically the input side capacitance of the receiver. Typically, it happens to be about 5 to 10 picofarads. Now, what happens is that if you're applying a voltage across here, between these 2 points, if I am applying a voltage, it gets divided between CB and CGTX. So if I'm applying a 5-volt voltage between this point with respect to this point, the 5-volt will be divided between CB and CGTX. Because this value is lower compared to this value, most of the voltage will get developed across this point. Only 1/100th of the voltage will be developed across CB. So the voltage on the body is around 50 millivolt. And this voltage is further divided between CL and CGRX. And a portion of this 50 millivolt will get developed across CL, which is detected. Okay, so considering the ratio of 10:1, only 1/10th of the voltage will be detected, which is 5 millivolt. Is this arrangement clear? It cannot be a DC. It is a signal. It's a switching signal. And the switching signal is used to send the data. So if you want to send some 0101 data, you modulate this. See 0, 5 volt, 0, 5 volt. You modulate the data and decode it. Is it clear? Okay. So yeah, that's how it works. But in reality, it is not as simple as that, because so here there are capacitors. So this is a very simplified model. But in reality, there will be capacitors between the signal electrode to the body, receiving signal electrode to the body. There will be capacitor between the local ground of the transmitter to the local ground of the receiver. So the model is even more complicated than what I have shown. But to get started with human-body communication, this model is sufficient. And you can easily work out this model. And most of the time, if the frequency of the switching is low, this model work out to be true. Okay, so yeah, these are the different ways in which you can work with human-body communication. And in fact, it is called capacitive human-body communication, because what happens is the signal voltage is getting divided between the capacitors, and it is further getting divided between the capacitor, and it is detected. So this form of human-body communication is called capacitive human-body communication. Okay, so there are 2 different ways in which you can operate capacitive human-body communication. In the first case, both are wearable. Okay, so in the second case, one of the devices is wearable and the other devices is grounded. Say, for instance, if you want to communicate some data to a say a door, if you want to unlock a door, if you touch a door, the data gets communicated to the door. In that case, the receiver of the door, typically the door will be grounded. The circuit in the door will be grounded. So this is a case where the receiver is grounded. And this is a case where the receiver is left floating. So what is the difference? The difference is that if the receiver is left floating, there will be a capacitor here, CGRX. So because there is a CGRX here, the voltage across the body is further getting divided between CL and CGRX. So the voltage that you see at V0 will be a divided voltage of VB. But if this point was grounded, the voltage across VB will directly see at output. Okay, so if the receiver is grounded, you get good signals here. So typically, if there is a machine to which you want to transfer the data, the signal to noise ratio would be higher in this case compared to that case where both of the devices are wearable. So any questions? Yeah, so okay, I'm coming to that. So in the sense that these capacitors are parasitic and it can vary over time. So there's a chance that the signal that you're sending may not be what you get here. So yes, the bit error rate is lower in this case. I'll come to that in the subsequent slides. Okay, so there is another form of human body communication, which is called galvanic human body communication. So the way it works is, at the transmitter side, you have 2 electrodes. And at the receiver side also, you have 2 electrodes. And if you want to send some data, you modulate the voltage across this. So the voltage gets modulated across these 2 electrodes, which propagates through the body, and it reaches the receiving end, which is detected. Okay, so typically what happens is that you have this galvanic human body communication can be operated in 2 different ways. It can be on the body or inside the body. So this is the case when the galvanic human body communication is within the body. Okay, within the body, what happens is that you have 2 electrodes, and which resides inside the body, and it transmits the signals. So yeah, so this is how the signals propagate in galvanic human body communication. So the difference is that in galvanic, you have 2 electrodes in contact with the body at the transmitter and the receiver side, but in capacitive, you have only 1 electrode in contact with the body. Okay, and galvanic is the only possible human body communication if you are placing the device inside the body, because if you are placing the device inside the body, both electrodes will be in contact with the body. Okay, so there is a application for galvanic HBC. The nodes which resides in the body need to have a galvanic mode of operation instead of capacitive. Okay. Yeah, so this is how it works. So you have a transmitter, and you can consider that there is a resistive network in the body, and whatever voltage that you are getting applied here, a scaled down voltage will be seen at the receiver. And if you want to transmit data, say 0 and 1, you transmit 0 voltage, 5 voltage in a switching format, and it can be detected at this point to decode the data. Okay, so there's a problem of safety here. The current is going through the body. Okay, so typically what people do is you place a high value resistor here to limit the current so that it is safe for the human body. And this is a case. Typically, people use galvanic human body communication only when you want to implant the nodes in the body. And there's a safety concern for galvanic human body communication. So people generally tend not to use galvanic human body communication with human body. They use it with animals. Okay, so at least that's the case now. Okay, so this is a high-level picture of the difference between capacitive and galvanic. So you have a capacitive transmitter, 1 electrode connected to the body. The other electrode is connected to the earth ground through parasitic coupling. There is no real connection here. Same here. The receiver side, 1 electrode is connected to the body. The other electrode is connected to the earth ground through a parasitic coupling. Here, if you look at here, the transmitter has 2 electrodes connected to the body. The receiver has 2 electrodes connected to the body. Here, the signal to noise ratio or the channel quality is dependent on these parasitics. The parasitics between the transmitting ground and the earth ground, receiving ground and the earth ground, and these parasitic can vary over time. But here, it is not dependent on the parasitic, so the communication quality is higher for the galvanic human body communication. But as I said earlier, it injects current, so people generally tend to move away from it. Yeah, so this is a, for a communication standpoint, this is how it works. You have data, you do OK modulation. Yeah. Yes. So I have a slide on that. Okay, I have a slide on what is whether it will affect HBC or not. So I'll explain that. So yeah, any other question? This one here. So there is no ground here. It is just showing that there is a parasitic coupling. It is left open. So it is like if you have a mic here, the mic has a parasitic capacitor to the earth ground. So this is just modeling that. Okay. Imagination. Yeah, correct. So when you're applying a voltage at this point with respect to this point, this is how the electric field lines look like. So that is why they have drawn like this. Yeah, so from the communication perspective, it's similar to any other communication modality. You have a data which is modulated using a carrier frequency. Typically, the carrier frequency is less than 10 megahertz. The reason why the carrier frequency is lower is because if the frequency is higher, the body will act as an antenna and it will start radiating. So it will be very similar to Bluetooth or Wi-Fi. So typically, the carrier frequency is restricted to even lower than 10 megahertz, even lower than 1 megahertz. So that is the area of operation. You have a receiver. If this is a case when the ground of the receiver is connected to the earth, and typically you have a high-pass filter. And the reason why you need a high-pass filter is because the body is acting like an antenna, and the power lines signals can get coupled to the body. So if you look at what is the voltage of the body, it has a significantly higher voltage, and you want to distinguish that voltage with respect to the HBC signal. So you have a high-pass filter to remove the 50 hertz, 60 hertz noise. You have an amplifier. This is required because HBC signals are very weak. And then typically you apply a BPF and decode. This is to decode the OK data, decode the OK modulation and recover the data. So many communication methods are being used in literature, but this is a very straightforward approach to send the data. Yeah, now regarding the safety. So this is a concern many people have, particularly when you hear about human-body communication. So what human-body communication does, particularly capacitive human-body communication, I will not talk about galvanic. In the case of a capacitive human-body communication, what you're trying to do is you are putting some voltage on the body with respect to the ground. And this voltage is around 50 millivolt. Okay. But if you look at what is the typical voltage on the body, on someone's body at some point in time, it could be as high as 1000 volts or 2000 volts, or it can also go up to 3000 or 10,000 volts. So if you ask what is the voltage on my body, it could be 3000 or 4000 volts with respect to earth ground. So that is the reason why when you are touching a metallic object in a dry weather condition, the voltage, the charge that is getting accumulated on your body gets discharged. And this creates an ESD shock. So typically for a normal person, the voltage on the body is in the ranges of orders of thousands of volts. So 50 millivolt is not going to create any problem. Okay. So the second part, even if there is no ESD static accumulation that is happening, there is a power line coupling that is happening. So if you are looking to a human body, there will be power lines all over the ceiling. And these power lines are carrying 230 volts. They get coupled to the body through a parasitic capacitor, which is very close to the parasitic capacitor of the wearable to the ground in the orders of 1 picofarad. And there is a capacitor which couples this voltage to the body. And this body has a body capacitance of 100 picofarad. So the 230 volt is also getting divided between C1 and C2. And the voltage that the power line noise is inducing on your body is far higher than what a human body communication is inducing. So in normal cases, power line communication or power line coupling introduces more voltage on your body than an HBC voltage introduces. So the third reason why you can consider it as safe is it works very close to the way touch technology works. So most of you use capacitive touch technology to interact with your mobile phones. So the way the touch technology works is that you have an electrode. You apply voltage on the electrode, which creates an electric field. And when you place your finger very close to it, the capacitance between this electrode to your finger increases, and that increase in capacitor is detected. So the way it is detected is by applying a voltage at the electrode, which gets coupled to the body. And in human body communication also, you are doing the same thing. So the only difference is that in here, you are using this medium to transfer the data. Here, you are using this arrangement to detect your body. So you can consider this as a capacitive, this as a capacitive communication, whereas this is a capacitive sensing modality. Yes. Yes. So that will be on top of your 1000 volts. And this 1000 volt is something that when you are walking, and typically when you touch some conductive objects, it gets discharged to the ground. Yes. Okay, so yeah, I understood the question. So what happens is that the voltage across the body itself is some higher voltage, and on top of that you are applying some small voltage on top of that, which is getting detected here. So it will be 1000 plus 50 millivolt, 1000 volt, 1000 plus 50 millivolt, and so on, because this point is floating. So the voltage on the body, the absolute voltage on the body doesn't matter. Yeah. Yes, it interferes. Yes. So that's why we have a high pass filter here. Yeah, so you have a high pass filter here. The problem with power line coupling compared to ESD is that power line coupling is varying also. So it's difficult to, it interferes with your data, HBC data. Whereas ESD, it's static. The voltage is static, it doesn't change. So you can easily remove it. Okay, so these are some of the applications that people have been talking about in the literature for a long period of time, for the last 3 decades. So this is a case where you can share your contact information by just giving a shake hand. You don't need to give the contact card. The first paper by Zimmerman proposed this application. Recently, people have been proposing the application wherein you can have the camera on your pills, which when swallowed can do the endoscopy. If you have an HBC technology embedded into it, the amount of power that is consumed by the camera will be lower compared to any other technology. So you'll be able to send high resolution cameras, high resolution pictures for a long period of time. So this is another application called secure authentication. So if you have a node on your body, HBC node, and if a door knob has an HBC receiver, if it can detect the signals, you can unlock the door by just touching the door knob. You don't need to use your fingerprint. Yeah, so that's about that. Yeah. Yes. Right. Yes. There was a standard as a part of BAN, body area networks. But how much it is, what state it is right now, I have yet to figure that out. But there was a part of standard, part of HBC was included in the BAN, body area standard, IEEE standard. Yes. The problem is that this is a technology that works only in the lab. So it is not commercialized. And so people are still exploring how to make it work. Yeah. So that's about the application part, and I will go and explain about some of the research areas in human body communication. One is about the node form factor. How do you structure the wearables? And that is very important because if you look at the channel quality, it depends on the parasitics. So it depends on the parasitic CGTX and CGRX. If you want to increase the received voltage, the only way you can increase is by increasing CGTX and CGRX. You cannot play with CB, that is the body's capacitance. So the way you increase CGTX is by having a large ground on the wearable, so that it has a higher parasitic capacitor with respect to the earth ground. So people are trying to figure out how to improve CGTX and CGRX without causing the wearable to be bulky. So if you have a large ground, the quality of the signal will be more, but it will also cause the size of the wearable to be large. Yeah, so this is what Professor Sujit was asking. That the reason we propose human body communication is because it should sit with a wearable that is also monitoring your body information, body vital information. So for instance, if you look at an ECG, the way it measures ECG is by taking the potential difference between 2 points on the body. That is how you get the ECG signal. Now, the human body communication, what it does is it alters the potential of the body. So, thus altering the potential of the body will affect ECG sensing. That is one question. Second question is, in ECG sensing, there is also a concept called RLD, called right leg drive electrode, which is placed on your right leg typically to bias body's potential. So whether that can create problem to the HBC transmissions. So what is the interoperability? So typically the HBC doesn't cause any harm to the ECG sensing, because what HBC does is it changes the body's potential with respect to earth ground. And in ECG sensing, you are measuring the voltage between 2 nodes. So this is a relative voltage measurement. What HBC is doing is changing the voltage of the body with respect to the earth ground. So it doesn't affect. But having a right leg drive electrode can affect the HBC. So it can affect the quality of the HBC transmission. So how do you solve that problem? In some of the designs, you can get away with right leg drive electrode. So right leg drive electrode is typically used in ECGs to bias the body, so that the power line noise that is picked by the body is not seen in the ECG. So there are mechanisms by which you can avoid RLD, but the fact is that RLD affects HBC. But the other way, it doesn't happen. So yeah, so this is a group of researchers working on how we can use this medium to transfer power from one point of the body to another point of the body. That is, if you have an earbud and if you have a smartwatch, how you can use body to transfer the power from the smartwatch to earbud. The safety concerns are still there, and there are a couple of research labs working on this area, transferring the power through the body. So compared to HBC, in HBC you are just transferring the signal. Now power is transferred, but here you are actually transferring the power, which can be used to charge the earbuds. Yeah, so this is something interesting to look at. One of the major advantages of HBC is that it is more secure. Most of the field lines are distributed around the body, unlike Bluetooth or Wi-Fi. But there is a possibility by which you can hack into HBC. If you have a large metallic object nearby, some of the field lines can go into this metallic object, and there could be a capacitor between the local ground of this receiver to the metallic object. And the signal seen by the receiver, a part of it can also be seen on the metallic object. So if a hacker really wants to hack into it, it can be done. The only difficulty is that you need to have a large metallic object nearby. Yeah, so to summarize, these are the technology limitations. It is heavily dependent on environmental parasitics. So it is dependent on CGTX, CGRX, and C body, which are parasitics. You don't have any control over it. If you move from one point to another point, the parasitics changes. Depending upon the weather condition, also parasitic changes. It is affected by surrounding noisy sources because your body is acting as an antenna. It is picking up all unwanted noise sources. It is affected by nodes form factor and position. The nodes form factor dictates CGTX and CGRX. So it is decided by how big or small the node is. It requires specialized receivers because the voltage that you see here are in the orders of millivolt. How do you decode that? How do you amplify and decode that signal voltage? And yeah, because of these reasons, there is no HBC based products out in the market. Most of the work is inside the lab. But the reason why we should work in this area is because there's a lot of push for Internet of Bodies. A lot of nodes are going to be on the body. And this is one of the promising technologies which can allow the power consumption to be very lower for communication, which allows the wearables to last for a long period of time. Yes. Yeah, so there have been research studies on that. A couple of papers are already there, wherein they are using HBC to create a network on the body, similar to body area networks. It's difficult in the sense that even having a wearable to wearable communication is not so easy because the channel loss is significant. So to have communication between multiple nodes is even difficult. So, but there are research groups working on that. Yes. So yeah. So the idea is that the communication power can be reduced. Instead of having a radiative technology like Wi-Fi, if you want to send it to a smartwatch, you use HBC. The communication power can be reduced. So the computation still exists, whether it is Wi-Fi or HBC. The computation part still remains a problem, but the communication component of the power can be reduced. So so this part, galvanic, it is modeled as through the muscles, through the blood and so on. But capacitive is, you consider it as a large capacitor. Your body as a large capacitor. There is no propagation of electric field. It's just a capacitor division that you are assuming, because the frequency is very small. Here you can assume it as a parasitic capacitor. You don't need to model the internal parts of it. Yes. For capacitive HBC, no, it's not a factor. So this is capacitive HBC. It just follows this equation, irrespective of where you put. But in galvanic HBC, yes. If the distance is large, the attenuation will be more. So it can be modeled something like resistive lamp. It could be, there could be a slight difference in the signal. Yes. It will be different. It is continuous, but that 50 meters. Yes. In the case of capacity, it will be like there will be a signal. So the body's potential will be little higher than compared to Earth. It will not discharge because even if it discharges, there will be a voltage at this point. So there will be again voltage dumped to the body's capacity. So all these models are very simplified models. So in reality, there will be a lot of other parasitics that comes into play. Yeah. So if the body's voltage is higher, this is a transmitter. The transmitter's local ground sit very close to the body. So this voltage will also be higher. If there is 1000 voltage on the body, the transmitter will also be sitting at 1000 voltage, typically. So this electrode has a voltage which is slightly higher than the 1000. So the idea is that these local grounds will be at the same potential as that of the body. If the body's potential increases, the potential of the local grounds also increases. I'm not sure. So it's not well studied problem. So not sure. So based on the way the circuit works at a higher level, I can say that the potential at these 2 points will also go along with the body, because it is very close to the body and the parasitic capacitor between this point and the body is very small. So the answer is that it is not studied. So it's not studied. Not sure. I don't know. Yeah, could be. Yes. The cost part is basically incurred by the HBC receiver. If you have a receiver which can send with a resolution of a 1 millivolt, you can create an HBC setup. HBC TX is very simple. Right? Just do power modulation. The receiver is a difficult part, And based on my experience, I would say 10 bits per second or 100 bits per second is what you can achieve out of the lab. If somebody claims more than that, it's not something that we can believe. So 10 bits per second is something that we can achieve right now because of these problems, because of the mathematics problems. But there are people who have claimed a higher data rate with a modified communication technology. So even if there are noises on the body, say for instance, pseudo-random techniques, they are able to solve that problem. But most of them are inside the lab. So how it will perform outside the lab is not known. So the intelligence part is not clubbed with HBC. So this is only the communication part. If you look at here, it only serves this problem, the communication part. The intelligence part is still, see, it solves this problem, communication part. The intelligence part is still inside the cloud. One advantage is that if you have HBC instead of Bluetooth or Wi-Fi, since the communication power is low, you can use that power on for the computation or the intelligence part. So offloading can be done if you have HBC. Yeah. It would be same thing as for data. So the HBC doesn't alter that. HBC is just a communication technology. Yes. It's just a medium to transfer the data. You can club that in the data. So that can be done. So you can timestamp the data points. So if you are interested in analog circuits, so if any students are interested in analog, please do come and join the group. Yeah, that can happen even if it is not HBC, right? So even if it is Bluetooth or Wi-Fi also it can happen. And yeah, that's a possibility. And the reason why some people in the research labs are pushing this technology is because it is more secure. The signal range is lower, so such things may not happen. That's what they claim. But there's a possibility to activate it.